Hello. 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 Hello.
Hello, 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 hello. ഇല്ലേ? ഹലോ, ഹലോ, ചെക്ക്. ഹലോ, 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 ഹലോ. ഇല്ലേ?
ഇതിനകത്ത് സൈൻ കാണിക്കുന്നുണ്ട്, ലൈക്ക് സൗണ്ട് കേറുന്നതില്ല ഇവിടെ.
ഹലോ,
ഇല്ല.
ഹലോ, ഹലോ,
കേൾക്കുന്നു?
ഹലോ,
കേൾക്കുന്നുണ്ട്.
ഹലോ. ഹലോ, 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 ഹലോ.
Mike. Hello. Mike.
ചെക്ക്. ഹലോ,
ഇവിടെ തന്നെ ഷെയർ കോപ്പി ലിങ്കും ഉണ്ട്, വാട്സാപ്പ് ഉണ്ട്. വാട്സാപ്പ് കിട്ടൂല, അതല്ലേ. പക്ഷെ അത് നെറ്റ് ഒന്ന് എടുത്ത് മാറ്റി മറ്റേതാക്കാമോ? അല്ലേ, ഞാൻ എൻ്റെ ആണല്ലേലും എടുക്കാറ്. അത്
ഹലോ, ചെക്ക്. ഹലോ, ഹലോ, ഹലോ.
Good morning, all. Today we have gathered here for the fifth lecture, fifth memorial lecture of Professor M.C. Valsakumar. Last year also, we were here in December, I think last 2022 December. Um, so I think Academy of Physics Teachers Kerala has decided to keep Cochin University Physics Department as almost a permanent venue of this lecture series. So our resource person, Professor Sriram Kumar, Professor of IIT Madras, and teachers, respected HOD of department, Dr. Aldrin, teachers of the department, Professor Valsakumar's family is here. Mrs. Valsakumar, his relatives are here, and teachers and dear students. I would like to mention a few words about Professor Valsakumar. He was a distinguished scientist at IGCAR Kalpakkam for, I think, nearly 32 years. He's from Kerala. He hailed from Kerala, from Talasheri, and he completed his MSc from Calicut University campus. After that, he joined BARC training school. And for 32 years, he was a scientist at IGCAR. He retired as a distinguished scientist and division head there in 2012. So after that, he worked for 2 years as a visiting faculty at HCU, Hyderabad Central University, then IIT Palakkad. And in 2019, there was his sudden demise was there. It was unexpected. And he was an honorary member of APT, Academy of Physics Teachers Kerala. I think some of you may be familiar about Academy of Physics Teachers Kerala. It's a registered organization of university physics teachers of university and colleges in Kerala. So he was an honorary member, and he had conducted a few workshops for the physics teachers. And during his long tenure at IGCAR, he was famous as a researcher in both in theory and computational physics. In theory, he had important contributions in open quantum systems, in statistical mechanics. And in computational physics, he was very instrumental in establishing a computational facility, a high performance computational facility at IGCAR. And many research students in IGCAR and elsewhere were molded by him, including myself. And upon his sudden demise, his family put together an endowment fund, both at IIT Palakkad and with APT also. In IIT Palakkad, every year they have been conducting a science quest for 11th standard students every May. Okay, this year also they will be conducting that using this endowment fund. And in APT, we are conducting every year this annual lecture series. So the purpose of this annual lecture series, today we are having this fifth lecture. It's an annual lecture on theoretical physics. So the aim is to inspire some of the young minds, MSc and PhD students, particularly MSc students, to theoretical physics. So different aspects of theoretical physics we conduct every year this talk. So today's lecture is being presented by Professor L. Sriram Kumar, IIT Madras. He's a well-known cosmologist of the country. So in his busy schedule, he has agreed to come here, even though he had some difficulties health-wise in the last week. We proposed to postpone if it's needed, but he was particular that he should be here to talk to you. And on behalf of all of us, on behalf of APT, let me welcome Professor Sriram Kumar. Welcome, sir. And let me welcome all the teachers for the purpose of formality. Even though it's a combined program of physics department and APT, let me welcome all the teachers gathered here, all the students here. And sir will be available in the afternoon until 4:30. He will be here for if you have to, if you want to interact with him personally, he will be here until 4:30. Okay. So let me welcome Asha teacher here. She is the vice president of APT for the presidential address.
Good morning, all. Academy of Physics Teachers, as Professor Hari has mentioned, is a voluntary organization of Physics Teachers of Kerala. Academy APT organizes many lectures on core topics on physics, as well as organizes APT talent search examination for young students, basically graduate students. There are many activities which APT put forward for popularizing physics learning and teaching. And Professor Valsakumar was one of the, he was an honorary member of APT and was also a resource person of APT workshop. I was fortunate to have participated in some of the lectures delivered by Professor Valsakumar. And this Valsakumar Memorial Lecture, as Hari has already pointed out, was instituted by the family, friends, as well as students of Professor Valsakumar in order to keep up the spirit of Professor Valsakumar. He was an inspiring teacher. And Cochin University of Physics, Department of Physics, Cochin University, in association with APT, is organizing this program every year, and this is the 5th one in this series. And this will be, CUSAT will be the permanent venue of this program. And this is basically meant for the students. That's what Professor Valsakumar has imagined, like to enlighten students to take up science as a good career. I hope this talk by Professor Sri Ram Kumar will be one such thing. And I urge our student community to make maximum utilization of these lectures. Thank you. I welcome Charles to introduce Professor L. Sriram.
Dear all, it's in fact a pleasure to introduce and welcome Professor Sriram, who is a friend of the Department of Physics as well as ATPT. Sriram started, he's actually a professor at, as you know, he's a professor at IIT and a member of Gravitational and Cosmology team there. He started his career as a research scholar, as a PhD student at IUCA with late Professor Tanu Patnavan, and he worked on primarily on quantum field theory in curved space-times there. After PhD, he spent a few postdocs abroad, specifically one at Hebrew University with Professor Bekenstein, who was also the founder of black hole thermodynamics, and with Dr. Don Page at University of Alberta. And eventually, he joined Harish Chandra Research Institute as a faculty, and later moved to IIT Madras. And ever since, he has been working there. And he is primarily working on the inflationary scenario of cosmology. That is basically the study of how baby universe behaved when at the time of Big Bang or around the time of Big Bang. And specifically, he is working on various aspects of that problem, like constraining the present model of cosmology and generation of magnetic field and other exotic models. And also he's working on gravitational wave generation and associated things in early universe. And that is probably the topic of his today's talk. He has a long CV, so I have to write down a few points. And he also has a wide network of collaborations, including Nobel laureates like George Smoot and pioneers of cosmology like Starobensky, Alexei Starobensky, who passed away recently. And most importantly, he likes to direct and mentor students. In fact, most of his PhD students, I think all of the PhD students and other postdoctoral members are well placed in various institutions in India. And he has been a friend of this department. He visited the department last 5 years, like 3 times, I think. And he gave talk each time and interacted extensively with the students. And today we have a great opportunity for students and researchers to interact with him, probably in the afternoon, as we said before. And so it's my pleasure to welcome you to the department, and I will pass over the mic to you. Thank you.
Check. Thank you, Charles, for a very generous introduction. I should begin by thanking Professor Valsakumar's family, as well as the Academy of Physics Teachers, Kerala, for inviting me to give this lecture. It's indeed a privilege and an honor to give this lecture. And as Charles mentioned, I've been here at QSAT a few times before to examine thesis, to give talks, etc. So I'm very glad to be back here giving a talk to students about gravitation and cosmology. At the largest scales and at the greatest strengths, the theory of Newtonian gravity that you may be familiar with ceases to be applicable. You require to explain the physical universe in these situations, you require a relativistic theory of gravitation, a theory that merges notions of space and time. One such theory, as you may know, is the general theory of relativity. In a relativistic theory of gravitation, gravitation manifests itself as curvature of space-time. The gravitational waves that I will be talking about are ripples in the curvature of space-time. And I'm sure you have heard over the last decade, we have been able to detect gravitational waves from merging compact binary black holes. And very interestingly, over the last few months, after collecting data for about 15 years, the so-called pulsar timing arrays have seen imprints of what is known as a stochastic background of gravitational waves. In this talk aimed at students, I will initially try to explain, put together essential notions of special and general relativity, and I will explain what gravitational waves are. I will also try to describe the detection by LIGO, and then finally, I will talk about what is that the pulsar timing arrays have seen, and why do we believe it implies a stochastic background of gravitational waves. I will explain the term stochastic background, etc., as I proceed. Evidently, the scope of the lecture is fairly big, and I need to start fairly low, and I will try my best, to ensure that I take you along as I narrate the story. Can we have this AC off? It's blowing right at me. I just need to turn this off, right? Yeah, done. Thank you. I think that should be fine. Thank you. So, we need to start with Newtonian gravity. I will make a few quick remarks to essentially highlight the difference between Newtonian gravity and what will be a relativistic theory of gravitation. An electromagnetic theory has to come in because that's, as you may have learned, is the route to special theory of relativity, and the special theory of relativity is the route to general theory of relativity. As I mentioned, gravitational waves are ripples in the curvature of space-time. There are some similarity with electromagnetic waves. There are important differences. The electromagnetic theory, I will comment about, is a linear theory. I'm sure you have learned what electromagnetic waves are. In contrast, gravitational waves are not exact solutions. They are approximations. They are small deviations from the space-time. And then gravitational waves, until a decade or more back, we weren't very sure whether we will be able to detect them. But there has been tremendous progress since the original discovery or detection of gravitational wave by the Laser Interferometric Gravitational Wave Observatory. Since the original discovery, there have been many such, detection of gravitational waves from merging binary black holes and even some neutron stars. And I will just very briefly touch upon the original discovery to highlight what is that has been observed what could possibly be its implications. And then I will talk about the observations by the PTAs. PTAs are the pulsar timing arrays, and why the recent detection, recent observations by the pulsar timing arrays suggest that there is a background of gravitational, stochastic background of gravitational waves. If indeed there is a stochastic background of gravitational waves, I will try to describe how it has, I'm sorry, I shouldn't have disturbed this, how it has important implications for the physics of the early universe that Charles was mentioning that I largely work on, and I will just provide a very brief outlook. So we start with Newtonian gravity. Let's recall the essentials. Well, you have Newton's second law. What it essentially says, mass times acceleration is equal to the force. Force is some external force. And it is important that you write this Newton's second law in certain frames of reference. You cannot be writing in arbitrary frames of reference lest you introduce what are known as fictional forces. You cannot write in a rotating frame or an accelerating frame. You need to write them in what are known as inertial frames of reference. And once you choose to write the equations, this equation inertial frames of reference, you can write in any inertial frame you choose to, you choose to work with. And in whichever the frame you are working in, the equation of motion will have the same form. And this is in some sense what is known as the principle or the Galilean relativity. In Newtonian physics, time is absolute. The clocks in whichever frame you're looking at, when I talk about different frames, you can think of yourself as standing at the bus stop, while there is another friend is in another, the frame of a bus, which is moving at a constant velocity with respect to you. And these are two inertial frames, and the time is absolute. You measure the same time as the time measured by, by a clock, the watch of your friend in the bus. And where capital V is the velocity of the bus in this example, and this Newton's law is sort of invariant under such a transformation. And you also familiar with the fact that this leads to so-called Galilean addition of velocities. The velocities add. If the friend is walking in the bus, his or her velocity is the sum of her velocity with respect to the bus and the velocity of the bus, and so on. That's on one hand. Here, the forces on the right-hand side could be any force. These could be electromagnetic force. This could be the gravitational force. And you're familiar with the Newton's inverse square law of gravitation. What it says is that if you have two masses, a large mass m and a small mass m, which are separated by a distance small r, then this is the force of attraction between them. It's proportional to the product of the masses and inversely proportional to the square of the distance between them. And it is an attractive force. It's radial in nature. The direction of the force is along the line connecting to the two objects, and the force is attractive in nature, as indicated by this minus sign here. Now, we will see in, the question is, if I have a relativistic theory of gravity, will I have a Newtonian force? How will I describe gravitation when I take into account so-called relativity? These are the points we will discuss as we proceed. If I merge the Newton's second law that I had a couple of slides back, and I use the Newtonian inverse square law of gravitation to be the force of attraction between two objects, such as the Earth and one of the planets that is moving around it, I arrive at famous Kepler's law. So the Newtonian theory of gravity and the Newton's second law seem to work well. It is able to explain all these Kepler's laws, the three Kepler's laws. I don't need to read them out for you. I'm sure you're all familiar with it. And for instance, it says, the first one says the orbit of a planet around the sun is an ellipse with the sun at one of its foci. But is this true observationally? Well, we'll come to that slide later. What you need to do when you have an object, that is moving in a force field, you have a complete system where you have to describe the field and, you have to describe the motion of the object. One is an equation of motion like the Newton's second law, and the other is the field generated by this object. Conveniently, here in Newtonian gravity and Newtonian physics, we describe if it is a gravitational field, we use the inverse square law. But you actually have an equation of motion that governs the field on one hand, and you need an equation of motion to govern the trajectory of the field, of the particle on the other. And in in the context of gravity, actually, the field is described by an equation such as this. I'll come to that in a minute. Since you may not be familiar with that Poisson equation, in gravity, there is another equation that you are familiar with in the context of electrostatics. You're familiar with the fact that the Coulomb's law also is an inverse square law, very much like the law of gravity. And it is not surprising that the Poisson equation that you encounter in the context of electrostatics can also be used to describe the gravitational potential phi. There are some crucial differences. Well, the rho here is evidently the charge density. There is a different constant which is related to electromagnetism, which is the permittivity of free space. In contrast, here you have the gravitational constant that plays a role in solving the Newtonian potential. Now, you know that the force is the gradient minus the gradient of the Newtonian potential. So if you solve this equation and take the gradient of the Newtonian potential from this, assuming rho here is the mass density is described by a point mass, you will arrive at the familiar Newton force law. And this is the equation of motion governing the gravitational field. So what you are essentially solving for is, on one hand, the trajectory of a particle, right, influenced by a gravitational field. And the gravitational field itself is described by an equation such as this, which is the Poisson's equation. But there is a problem. In Newtonian physics, you have this, the force that is generated by this gravitational potential is instantaneous. The moment I change the mass here, it is felt at any farther away point instantaneously. That, as we shall discuss, is inconsistent with special relativity, and therefore this cannot describe a relativistic theory of this cannot be applicable when you take into account relativistic effects, and you need to modify this equation. I talked about just a couple of slides back how combining Newton's second law with Newton's law of gravitation leads to my Kepler's third law, and everything is fine. Not quite so. You look at the perihelion, the motion of the perihelion of Mercury. I presume you know what is Mercury. It's the closest closest planet to the sun. And you look at whether it comes back to an ellipse, whether the trajectory of the Mercury is an ellipse, whether the perihelion, that is the point of closest approach, comes back to the same point. Well, it does not. What you find is that this perihelion keeps shifting. Notice, this is one of the axes of the ellipse, right? What happens is that as time progresses, instead of coming back, the Mercury coming back to the same elliptical orbit, the major axis of the ellipse starts shifting slowly, or in other words, this perihelion, which would have been here, it starts shifting slowly. And you need to explain this. Now, if you recall, when you derive Kepler's third laws, you are essentially assuming that the planet is in motion around the sun, and you essentially ignore the effects of all the other planets that are present. Well, there is a huge planet such as Jupiter that is present, there is Saturn that is present, and you can, they indeed have an effect on the motion of the planets inside. And you can calculate what those effects are. This has been done in the 19th century. And what one finds is that the precision is about, 5,600 seconds of arc per century of Mercury. Of this, you're able to explain a good fraction of it by taking into account two effects: the presence of the other planets, and the fact the sun that you think is a sphere is not quite a sphere, it's a spheroid, and it induces corrections to your Newtonian potential, and you need to account for them. And most of this you're able to explain using Newtonian gravity and Newtonian physics. But you're not able to explain about 43 seconds of arc per century, the precession of perihelion of Mercury by 43 seconds of arc. As we will see later, this plays a crucial story in general theory of relativity. We'll come back to this story. So not everything is hunky-dory with Newtonian physics and Kepler's laws. So this is one strand. I need to construct different strands, very much like a braid. I need to bring these different strands and build my story. What's the other strand? Electromagnetism. You're familiar with electromagnetism. Unfortunately, what happens is that most of the textbooks spend a lot of time on electrostatics and magnetostatics, and towards the very end, they tell you electromagnetism is a relativistic theory. If you look at Landau Lifshitz, it starts by arguing it's a relativistic theory. Let's get on with it. Construct a relativistic action, vary them, and arrive at the equations of motion. Well, I'm sure you're all familiar with the Maxwell's equations of motion. And this is, this theory is a relativistic theory. What does it mean? If you want to understand how E and B are related, I talked about how you need to work with inertial frames when you write equations of motion for Newton's second law, leading to Newton's second law. Now, you know very well, if I have a point charge at rest, I have an electric field, right? The moment I start moving, what do I see? I don't only see an electric field. I also see a magnetic field because of the fact that the point charge is no more at rest in this new frame. It is moving, and therefore it has a current. And in a complete theory, relativistic theory, you can show how the electric and magnetic fields are related. They are related by something called a Lorentz transformation, which I will talk about a little later. So Maxwell's equations emerge from a relativistic theory, and rho is the current density. Charge density. J is the current density. And if you consider a situation where rho and J are absent, right, and you try to solve these equations consistently, you obtain non-trivial solutions, which are called electromagnetic waves. I hope you understand, why I need to talk about electromagnetic waves, because I will be talking about gravitational waves later. Let me emphasize this again. All you need to do is that you need to set in the set of Maxwell's equation, which is a relativistic theory, you set rho and J to be 0. There are no sources. Even in the absence of sources, you can have non-trivial solutions. You can combine those set of Maxwell's equations to arrive at an equation such as this, which has non-trivial propagating solutions, which what we refer to as electromagnetic waves. And you also know that electromagnetic waves are transverse. They propagate at the velocity with the velocity of light. That you can convince yourself by constructing solutions to this equation. I'm sure you would have done it already in one of your courses, or you will be doing it soon. And what you find is that this is the direction of propagation of the electromagnetic wave. The electric field is in a direction perpendicular to the direction of propagation. And you can again show using the Maxwell's equation that the magnetic field is in a direction perpendicular to both the direction of propagation and the direction of the electric field. And the direction of electric field tells you the polarization of the electric field, okay, of the electromagnetic wave. So if it is in one direction, it is oscillating. The electric field is going up and down, but the direction remains the same. You have linear polarization. You can typically have, one polarization like this and another polarization like this. It is transverse because the polarization is in a direction perpendicular to the direction of propagation. We will see much later that the gravitational waves are also transverse waves, but they have different, a little more complicated type of polarization. Let's come back to the electromagnetic waves. They have polarization either in this fashion or in this fashion, or they can also have more complicated polarization, what are known as, circular polarization. The polarization can go like this, or they can go like this, okay? And, but the bottom line is that the electric field that, determines the direction of polarization, and there are two linear polarization, or you can have superposition of these two basic polarization states. And as I already mentioned, they travel at the speed of light. They are transverse in nature, and with their polarization being determined by the direction of the behavior of the electric field. What are the sources of electromagnetic waves? What you will, the electric field that you're familiar with is the Coulomb field. It goes as 1/r². But you will learn, when you solve for the complete set of Maxwell's equations, when a charge which is accelerating, undergoing non-uniform motion, right, then you will find that in addition to the standard Coulomb field, there is a 1/r field, which is known as the radiation field. And often when you have this radiation field arises when you have non-zero acceleration. And for instance, if you have a collection of charges which are just oscillating radially, they will not emit electromagnetic waves, because outside, if it is just oscillating radially, what happens is that, according to Gauss law, you can immediately show that the field is just the standard Coulomb field. There are no additional possibilities. Okay, so what you need is essentially a dipole. You need a dipole. For instance, the most dominant radiation in the context of electromagnetism, if you have a charge distribution with a time dependent dipole moment. So if you have two charges which are exhibiting oscillations like this, they will emit electromagnetic radiation. And one such simple source is a rapidly accelerating charge. And most of the astrophysical sources of electromagnetic radiation, classical electromagnetic radiation, is because of accelerating charges. So that is what we have in the context of electromagnetic waves. Now we need to move on to a slightly different step towards special theory of relativity. And until the late 1900s, people believed you need a medium for anything to propagate. So if you want light to propagate, you need ether or some strange object in which light has to propagate. And I'm sure you're familiar with this famous Michelson-Morley experiment. And this Michelson-Morley experiment will play a major role when we talk about detection of gravitational waves by LIGO, about 10, 15 slides down the road. So what do you have? You essentially have a source, a light source, right? And it is sent through two paths. There is a beam splitter. It is sent through two paths, okay? And then it comes back, and what you do is that, so there is a source here, there is a beam splitter, it goes through two paths, and often it is sent back and forth many a time. And then eventually what happens is that somewhere on one side, in the same side as the light source, you receive the light, and you make them interfere, and you look at the interference pattern. And this is a typical interference pattern. I'm sure you have heard about the story of the Michelson-Morley interference matter. What happens, the suggestion was that there is an omnipresent ether which sort of helps light propagate. And if you are on the surface of the earth, you may be, as you are traveling on the surface of the earth, there will be an ether wind which is blowing ahead of you. All right. And what Michelson and Morley did was as follows. They first, I moved in the wrong direction. They first set it in one direction, and then they turn this table by 90 degrees and essentially examine whether there is a change, there is a shift in the fringe. And if there is indeed ether, and you have a Galilean addition of law of velocities, that you are either flowing with the ether, light is flowing with the ether as you are traveling in this direction, while on the returning, it is flowing in the flowing along with the ether in this direction, while you have in the forward direction, light is flowing against the ether, and you apply Galilean law of addition of velocities, there ought to be a fringe shift. And there was no fringe shift observed when Michelson and Morley first set up the experiment in one direction, and then twisted this table by 90 degrees and compared the fringe shift. And what you can do is that to increase the sensitivity of the fringe shift, all you need to do is to increase the path length. The larger the path length, the larger is the fringe shift. What Michelson and Morley initially worked with a 1.2 meter table, and then later they set up a situation where these they increase the path length by making these beams go and back and forth many a time. I think the final result was where the path length was about 11 meters or so. So essentially they did not see a fringe shift, and you need to understand its consequences. And this is where Einstein comes in with special theory of relativity. What you are essentially told is that we don't need to worry about ether at all, and the speed of light is the same in all inertial frames. You don't need an ether for light to propagate. And this first law is not so difficult to understand. The laws of physics have the same form in every inertial frame of reference. There is a notion called covariance. That is, when you write F equal to ma, it's a vector equation. And this equation is valid in any inertial frame of inertial frame of reference. And remember, this is essentially the Galilean relativity principle that has been restated by Einstein. But there is something non-trivial which is in conflict with the Galilean law of addition of velocities, which is the fact that the speed of light is the same in all frames of reference. And as I already mentioned, the first of these postulates is essentially the original principle, relativistic principle due to Galileo. The second is in conflict with the Galilean law of addition of velocities. And what you need to do is that, if you recall earlier in my very first slide, I had a relation between the time and the position of these two observers, you in the bus stop and your friend who is traveling at a constant velocity along the x direction in a bus. And there the time was absolute. This is no more so in special relativity. I'm sure you have learned about the so-called Lorentz transformation that relate the coordinates, say t prime, x prime, y prime, and z prime, which are the coordinates with respect to this observer in the bus, to the coordinates of the person, of the observer who's located at the bus stop. And where gamma is the standard factor and c denotes the velocity of light, and v is of course the relative velocity between the two frames. And there are many consequences of special relativity. And what you thought in Newtonian physics, simultaneity was absolute. We will say we'll reach here, we'll start the lecture at 11, and we'll all come here and start the lecture at 11. You can quickly argue, using the fact that the velocity of light is the same in all frames of reference, the concept of relativity, the concept of simultaneity ceases to be absolute. It is relative, and there are additional consequences such as Lorentz contraction and time dilation, which I don't have time to discuss. So one of the important concepts which will carry forward from special relativity is this idea of space and time. You have seen in the last slide where the coordinate transformations mix space and time, and you will have this notion, this diagram that space-time diagram that you see often in the context of special relativity. You are, say, sitting here. If you're sitting here, the time, you can't stop the flow of time, therefore you flow. So what you have done is that you have essentially suppressed one dimension, and you have one time dimension and two space dimensions. You often set C to be unity so that the dimensions of space and time, space and time have the same dimension. And so this is vertical axis is time, the horizontal axis of space. And what you have is that if you are sitting here, this will be a path light cone. What it implies is that any event that happens within the past light can influence you, and you can in turn influence any event that is within your future light cone, but you cannot influence anything that happens beyond this light cone. And in the context of general relativity, you still have concepts of light cones, but they don't remain cones, and they will get modified depending on the geometry. And this is what general relativity is all about. So we have come a long way from Newtonian gravity to special relativity, and we are trying to understand what general theory of relativity is. One of the important concepts in general relativity is the so-called equivalence principle. It is not very difficult to understand. Think of a situation where you have a uniform gravitational field, such as on the surface of the earth. Okay, and there is this student who is playing with a ball. When he or she drops the ball, it falls. Okay, imagine another situation where you are far away from the earth, but there is this rocket ship which is moving, accelerating, in fact, at the same acceleration as your familiar acceleration due to gravity. What will happen if the student drops the ball? It will fall exactly in the same manner as on the surface of the earth. So there is an equivalence between certain accelerated frames and gravitational fields. So then this raises the question, if I have a gravitational field, can I construct an accelerated frame such that the gravitational field goes away? Can I always do that? Let me repeat this argument. So what you have here is as follows. You have Earth, right? And here, you know what happens. You've played with a ball many a time. What happens on the surface of the Earth will also happen in the confines of a spaceship which is moving with the same acceleration due to gravity. If this person carries any experiment within the spaceship, it will resemble the experiment carried on the surface of the earth. There is another way of stating this equivalence principle. It's the famous Einstein's elevator argument. Imagine a situation, right? Imagine a situation, I went in the wrong direction, right? So imagine a situation where there is a tiny elevator. I have drawn a large elevator. Think of a tiny elevator that is falling, freely falling, right? And what will happen is that if you drop a ball, how will it look? If the elevator is not falling, it is subject to gravity. It's like, staying on my room and dropping the ball. Its consequences. But if the elevator is falling at the same rate as the acceleration due to gravity, what will happen? The frame will be inertial. The ball will just remain with you. So in other words, what you have done is that you have a gravitational field, that of the earth. Had the elevator been static, you would have felt the gravitational field of the earth. But you fall, so to say, at the same rate as the acceleration due to gravity, you stop seeing the effects of gravity. You become inertial. This is exactly the opposite of this example where these are equivalent. So what you can do is that you can freely fall in a gravitational field and thereby become inertial. But can I do that in a gravitational field elsewhere? Then I can remove gravitational field, if this is indeed true, by just choosing to work with accelerated observers. Not quite. And this is what this example illustrates. Okay, the fact that you can locally remove the effects due to gravity, but you cannot remove it completely. How do I illustrate this? Think of a very large elevator. The radius, the size of the elevator is comparable to the radius of the earth. What will happen if I drop balls in such a large elevator over a period of time? If it was a small elevator, it will just stay with me as I am falling. And therefore, it's like, ball which is next to me in the absence of gravity in an inertial frame. But if I have a large elevator, I am here and Charles is on the other side of the elevator. What will happen is that he will see the ball staying next to him and I will be seeing the ball next to him. But what is happening is that because of the curvature of the earth, right, the balls are actually falling like this, not in a straight line. What it implies is very simple. If you are carrying out experiments much smaller than the typical curvature scale, it will look like as though there is no gravity. But you carry out experiments on scales comparable to the curvature, right, you will see gravity. It's no different from the fact that this room can be described by Euclidean geometry, this floor of this room. Okay, but if I try to determine the distance between here and Chennai, I have to account for the fact that I am on the surface of the earth. I cannot ignore the curvature of the earth, and I have to take into account the curvature effects. Okay, so gravity can be made locally flat. You can remove gravity locally, but you cannot remove gravity globally everywhere. In other words, gravity manifests itself as curvature of space-time. This is essentially what Einstein's equations tell us, and there is a famous quote by Wheeler. I will just mention it in a matter of minutes. What happens is as follows. This is the fabric of space-time. This rubber sheet is the fabric of space-time. The moment I place a big ball in this fabric, think of this as a rubber sheet, it dents my space-time. It warps, it modifies the space-time around the big mass. And now if I drop a marble around it, right, how will it move? It will move in these, warped fabric that has been created by this big mass. Okay? So there is this famous quote I was mentioning by Wheeler. It says, matter tells how, space-time how to curve. I place a large matter, it curves my space-time. It determines how space-time curves. And the curved space-time, so I place a mass, I have a large black hole. What it does is that it changes the fabric of space-time around it, That's a matter tells space-time how to curve. That's one part of this statement. And that's what we refer to as the Einstein's equation. Now, in this curved space-time, I throw a marble. In this curved fabric, this curved fabric which has been curved because of the presence of two large black holes, I throw a marble. The curved space-time tells how the marble to move. Okay? So, just like in the context of electromagnetism, you will have two sets of equations. One set of equations are the Maxwell's equations, which tell what the electric fields are given charge and mass densities. So, given these large masses, you know what the gravitational field is. What is the curvature of space-time? Given the curvature of space-time, right? Let's go to the Maxwell's equations. Or the context of electromagnetism. Given the electric field, I know how to determine the motion of charges. I just need to apply Lorentz force law. In a similar fashion, if you're solving Newton's equations, which tell how the space-time around these big masses are curved, I can arrive at what is known as the geometry of the space-time. With the geometry of the space-time at hand, I can determine how a marble placed in this space-time will move. And that is actually known as the geodesic equation. And they form a complete set of equations that I can solve. Now, it's very difficult for me to establish how general relativity solves the problem of the precession of perihelion of Mercury. I told you we were able to explain everything about 5,600 seconds of arc of the perihelion of precession of the perihelion of Mercury. I'm able to explain using Newtonian physics, namely effects due to additional planets and the oblateness, or the fact that the sun is not truly spherical. You can take into account relativistic effects. Okay, and there are simple exercises. If you are interested, I can give you these exercises after my lecture. Okay, and you can show, if you take into account additional potential terms, you can indeed explain the 43 seconds of arc per century, and this actually arises from general theory of relativity. And this is one of the early so-called successes of general theory of relativity. There are other classic tests of general theory of relativity I don't have time to go into. One of them is gravitational lensing. Light is bent by the gravitational field, and this is a famous Einstein cross, where the same object is seen 4 times because a farther away object is lensed by an intermediate object. And another is something called gravitational redshift. As light emerges from a gravitational field, it loses energy, and therefore its frequency redshifts. And this has been actually observed in the laboratory. There are various tests that confirm that general relativity is in the right direction. Now, I've built everything to introduce you to the idea of gravitational waves. What time did I start? 11:20, right? 11:15. Okay, all right. I'm on time, I believe. Okay. So now we need to understand gravitational waves. What are gravitational waves? Well, they are small disturbances in a given space-time. I illustrated the space-time as a rubber fabric a few slides back. You saw this rubber fabric where there was 2 big masses placed, and then there were, they created dents in the fabric. What it means is that the presence of masses changed the geometry of space. And gravitational waves are small disturbances. Think of a taut rubber sheet, and you just pat it, and you will have these ripples propagating in this fabric, rubber fabric. And these are essentially gravitational waves. They are small disturbances in a given space-time, much like ripples in water, and they travel at the speed of light, because in some approximation, they essentially reduce to the equation for the equation which is similar to the equation of electromagnetic waves. And the gravitational waves are transverse in nature. I told you what transverse means. They essentially oscillate in a direction perpendicular to the direction of propagation, and they have 2 degrees of polarization, but they have slightly more non-trivial, the polarization is slightly more non-trivial. I'm just going to give it illustrated with the help of an example. I'm sorry, with a GIF file. Okay, there are 2 types of polarization. So what happens is as follows. If you have if you have a ring of objects, imagine a ring of objects, ring of marbles, tied together through a bead, and a gravitational wave passes through perpendicular to this direction, there can be, one type of polarization will make this ring of marbles oscillate in this fashion. And this evidently is called the plus type uh, polarization. And there is another type of polarization which makes this ring of marbles, ring of masses, move in this fashion. And obviously, it's called cross type of polarization. And so in general relativity, these are the two types of polarization that are possible. Unfortunately, my animation is not working directly in this file. So there is one more point I need to make. I talked about how you can have dipole radiation in the context of electromagnetism. If you have a dipole, for instance, if you have a radially oscillating star, it will again not emit gravitational wave radiation. You need a non-trivial quadrupole. Okay, so you have a varying quadrupole moment. If you have masses whose quadrupole is varying, just like the quadrupole definition is the same definition that you may have encountered in the context of electromagnetism. When you carry out the multipole expansion, instead of the charges there, you replace them by masses. That's all. If you have non-trivial variation of the quadrupole, that system will emit radiation. And this is essentially occurs because of the fact that conservation of mass forbids monopole radiation, and conservation of energy and momentum rules out dipole radiation. And this is one of the crucial differences between electromagnetism and gravitation. And the gravitational waves are exceptionally weak. So you need very, very strong sources. If you want to detect, gravitational waves of detectable strengths, you need extraordinarily strong sources. And there is this, cartoon by Sidney Harris where, because of the enormous amount of gravity, they're playing baseball. The gravity is so strong, the ball that you hit can't go very far. So in a similar sense, you need extremely, strong sources for generating gravitational waves of adequate strengths. When I mean adequate strengths that can possibly be detected by detectors on the Earth, you can have rotating neutron stars. They are still not detectable. They can be exploding supernovae. Some of them can be detectable with our current strength of detectors. Coalescing binary neutron stars or black holes. This is what we have been able to detect. I will discuss one example in some detail. And supermassive binary black holes at the center of galaxies, you have huge black holes with masses of 1 million solar masses or larger, and they can merge and they can emit gravitational waves, and they can be detectable. And as I will talk later, these can be generated through quantum fluctuations in the early universe. And you can detect them at different ranges. So what I'm going to talk about is essentially these two. This is the frequency. So you're talking about 1 hertz here, right? 1 hertz here. LIGO measures at about 100 hertz or so, all right? And I will talk about, I didn't mean here, I will talk about detection here by terrestrial interferometers, that is laser interferometric gravity wave detector, which measures at frequencies of the order of 10 to 100 hertz. And I will also talk about pulsar timing arrays, which measures in the nanohertz of range of frequencies. It's a completely different story about how you can detect what are known as primordial gravitational wave through its imprints on something called the cosmic microwave background. That's a different story. I will not talk about it here. So now we are coming to the main theme of the story. What are these observations by LIGO? What is LIGO? It is essentially the same Michelson interferometer that I talked about earlier, which was constructed more than 120 years back. Remember, if you want to measure small, even tiniest of disturbances to the mirrors, what you need is an adequately large phase shift. Okay, if you want a large phase shift, what does it depend on? It depends on the path length. So if the gravity waves are extremely weak disturbance in space-times, What is a disturbance? As I move my hand, I generate gravitational waves. In principle, this bottle is shaking, or the water in this is shaking because of the gravity wave generated. But just that, the gravity wave generated by, seem massive, but not adequately massive to generate black holes. I'm sorry, generate gravitational waves of adequate strength to move this water inside. Okay, and so they are extremely weak gravitational waves coming from faraway reaches of our universe, and they make the mirrors in this Michelson-Morley interferometer move. And our goal is to detect the smallest of such movements. And evidently, I need a large path length. So what do? I construct a very large Michelson-Morley interferometer, and that is essentially, you have each of these arm lengths which runs about 4 kilometers. You just don't stop there. You want to increase the path length. So what do? You make the slide go back and forth. Remember, I told you, even in the good old Michelson-Morley interferometer, the desk was just 1 meter or so. But Michelson and Morley made the slide beam go back and forth to increase the path length. Go read AP French relativity or something. They will tell you how the path length is proportional to the phase shift. Okay, so they increase the path length from 1 meter to 11 meter by making it go back and forth. Here, the LIGO makes them go about, I think 300 times or so. So the path length actually is something like 1,200 kilometers. And what happens as a result here is, where I would play a very famous movie originally due to LIGO. Let me try to get that for you. Seem to have closed that window, unfortunately. This is a very popular movie. That's Rainer Weiss, one of the persons who, created this idea of LIGO and won the Nobel Prize. So I'll just stop this video. So what we have is the LIGO detector, and this is just an illustration of what that video showed. As the gravity wave hits the detector, so what essentially you can see here, this is the original length of the arm. One arm is stretched, okay, like if the gravity wave hits it in this fashion. And now what happens as the gravity wave, goes to another part, changes by its phase. So one part of the mirror is pulled in, another is pushed out, and they brought back to the original position. And this change in the interferometer length shifts the location of the fringe shifts, and which allows us to understand what is the strength of the gravity wave that has been hit. I will just play another video which illustrates the manner in which, what is the nature of the gravity waves that has been generated through the coalitions of two black holes. What we have in mind are two, why is this? So there are two black holes which are merging, and please note here, it's still not, the gravity wave is still not emerged from this. Can you see this blue line, which indicates the nature of the gravitational waves? What is happening is that as the black holes are merging, this is supposed to be the space-time, the fabric of space-time that I've been referring to. Those are evidently the two black holes. As they merge, what is happening? Their amplitude keeps rising and the frequency keeps rising as well slowly. And what you have is a chirp, very much like the chirp of a bird. And eventually they merge and to form a single black hole. And they have what are known as quasi-normal modes. They have slowed down the animation to show what happens very close to their formation. The movie is frozen. There is a single black hole that forms, and that's it. It just black hole quietens down, and there is nothing seen thereafter. And this is typically what is expected. These waveforms are nowadays generated through a mixture of analytical and numerical effects. And let me just close this movie. And what happens? So this is the original detection, in September 14, 2015, by these two detectors, one at Hanford and another at Livingston. They measured independently. They have moved one of these, waveforms on top of the other to show, and they have also compared. That's the original result. They have compared the waveform with results from numerical relativity. Those are details. This is the actual data as detected in the two interferometers at Livingston and Hansford, and you can see they match fairly well. And what is important is that you see that as the amplitude, this is the normalized amplitude, in some sense the strength of the gravity wave, or equivalently the strength of the shaking of the mirrors. And what essentially happens is that as the amplitude increases from blue to some yellow, you see an increase in the frequency as well. Very much that's what is referred to as the chirp. This is one of the this is actually the first original detection of gravitational waves from merging binary black holes. I'll just play one movie, just to complete all the arguments. Oops, I should have played it with another. I hope this is picked up there. No, not this one. I'm sorry. You should be able to hear the chirp. That's the chirp. That's all. For about 0.3 seconds. If you transfer, it's in the audio band. Had it been, you've been able to hear it with your ear, that's the manner in which you would have heard. For 0.3 seconds, there's a chirp, rising frequency and rising amplitude for a very short duration, which LIGO has been able to detect. And I should mention, since then, LIGO has detected or observed, to be precise, many such binary mergers. Each one corresponds to a merger, right? These two objects merge to become a larger black hole and so on. And there are many, many stories to say about this. But notice these are astrophysical sources of gravitational waves. Just like in the context of electromagnetism, there can be many sources of gravitational waves. Electromagnetic waves. This is because of wave emission, quantum emission from a star, classical emission from a moving charge in some other part of a galaxy, or this could be electromagnetic waves that emerge that were always present from the Big Bang. Do you know what they are called in the context of electromagnetism? It's called the cosmic microwave background. You can have a background of electromagnetic waves. You can have isolated sources of electromagnetic waves. And similarly, you can have isolated sources of gravitational waves, some of which we have seen as arising out of coalescence of very massive black holes. Now, we move on to this recent detection, or recent observation rather, by the so-called pulsar timing arrays. Let's start with what are pulsars. Pulsars are essentially extremely dense neutron stars. They are, end product of stellar evolution. I don't have time to go into that part. and some of them carry very strong magnetic fields, and they have a direction of spin, and their direction of magnetic field can be different from the direction of their spin. And you know, if you have magnetic fields, charges will be accelerated, and we just discussed as to how if charges are accelerated, they emit electromagnetic radiation, and these spinning pulsars emit extremely regular pulses of light, and their period can range from milliseconds to seconds. And what people have done is as follows. They've tried to hunt for what are known as gravitational waves using these pulsars. What they essentially do is the following. You have pulsars from different regions of the sky. And here it is, some of the pulsars are indicated here. And you observe the pulses arriving at from these different pulsars. And there are close to, I think, 3,000 pulsars are observed across the sky. So all you want to do is constantly observe the pulses coming from them and see whether there is any change in the regularity of the pulses. Okay, and this is called as the timing residual. I don't need to go into the technical details. All you do is observe the pulses from one direction, from one pulsar and another pulsar, and correlate them. As you can imagine, the pulsar are highly regular, and their pulses will hit you at regular intervals. But if there is a background of gravitational waves, I use the word stochastic and background. Stochastic means random. We don't, they are random. They can come from any different source. There is nothing relating one gravity wave hitting me today and another gravity wave hitting me sometime later. And it's background. What it means is that we are being hit, just like we are being hit by electromagnetic radiation. What are the sources of electromagnetic radiation? There could be anything. They could be charges, as I described, moving in a magnetic field in some part of a galaxy or faraway galaxy, or this could be quantum emission, in some region of the sky. Okay, and so all these are various random events that are reaching us. In a similar fashion, as I mentioned, anything that moves will in principle emit gravitational waves. The only thing is that the smaller the mass, the lesser is the strength of the gravitational waves. If you want gravitational waves of adequate strength, as I already indicated, if you want astrophysical phenomena, they need to be essentially coalescences of very massive objects. These could be, for instance, if you have black holes, different black holes, extremely heavy black holes, supermassive black holes that are merging, they will take a very long time to merge. And as they are merging in different regions of the sky, right, they will be emitting gravitational waves. And what will happen is that between you and the pulsar, there will be a gravitational wave that will be passing by. Okay, and as they pass by, they will cause a disturbance in the arrival time pulse of the pulses. What people showed is the following. You start correlating the arrival time of the pulses of two different pulsars and start correlating with every two pulsars in the sky. And you assume that this background of gravitational waves that are coming from, whose origins we do not know, are influencing the arrival times of the pulses. And they you have to integrate these pulses over a considerably long time. And when you integrate, they have integrated over for about, these pulsar timing arrays have integrated over close to 15 years or so. And what they have been able to show are two things. The first is that if you have an isotropic source of gravitational waves, that is, the gravitational waves are hitting you from all different directions of the sky, this correlation across two different pulsars will depend only on the angle of separation between the pulsars in the sky. Let me repeat. So all I do is that I collect pulses from one pulsar here, another pulses, all right, and I try to correlate them. You correlate something called the timing residual, okay, and it is just the difference between the expected time period and the actual time period. and you measure every time period. These are which means that virtually every second you have a data point, and you integrate over 15 years. Okay, and you know the locations of pulsars in the sky, where they are located, and you correlate. I think they carried out, as you can see, 2211 distinct pairings of 67 pulsars. Okay, and what you can these correlation that you are constructing will depend on two quantities which are completely separated. One is a function which is known as the Hellingsdowns curve. I don't have an analytical form here, but I can show the analytical form of it. And another which depends on the strength of the gravitational wave background. I'll wind up in 5 minutes. If I've gone over, please bear with me. Okay, let me repeat. One which depends on only the angle of separation between the pulsars. This is expected whenever you have an isotropic background. Even if you have learned about cosmic microwave background radiation, for instance, whenever you have an isotropic background, any correlation function will depend only on the angle of separation between these two pulsars in the sky. And what you have here, this black dashed line, is the theoretical Hellingsdowns curve, and this is the data point, and the data seem to suggest that there is a stochastic background of gravitational waves. What is the other thing? I told you that it also depends on the strength of the gravitational field, right? And what you are interested in, what is known as a power spectrum. And power spectrum are often characterized by two quantities. One is known as the amplitude. So you have a power spectrum. What it is? A quantity which is function of wave number. Okay. Often you characterize in terms of some amplitude, and you assume a simple power law form, and it has an index. Okay. And what the PTA observations have been able to arrive at an amplitude and an index. Both are well constrained. And now it's a matter of explaining what is the origin of this stochastic gravitational wave background. And this is where the early universe comes in. Okay, I'm just going to run through this in about 3-4 minutes. This is a timeline of a universe. So you have this curve, this picture, I'm sure you have all seen. What it describes is here, this thing here is the growth of the universe. The universe is expanding, right? Is the expansion of the universe. I should have been careful with my choice of words. Reflects the expansion of the universe. The expansion, there was a very rapid epoch of expansion, which is called inflation. That's what Charles was referring to as I work on largely. And then it is the fluctuations during inflation that gave rise to something known as the cosmic microwave background. There was something known as the dark ages, when there was nothing present. Okay, and then the galaxies began to form, etc. And what you are essentially seeing here is some imprints of events that happen around these epochs. There are various quantum phenomena that can happen early in the universe. For instance, inflation is driven by a scalar field. It's like a particle rolling a hill, okay? And as it rolls down the hill, this scalar field can make the universe expand extremely rapidly as here, okay? And what happens is that this ball, it's a classical field. It also contains quantum fluctuations, and it is those quantum fluctuations that generated all of us, all the structures in the universe. And at the end of inflation, what happens is that the universe is supposed to emerge through a process of reheating. During inflation, the universe cools tremendously. But if you want to continue with the Big Bang idea of the universe, you need to reheat the universe, and that is supposed to occur towards the end of inflation. Now, using such scenarios, you can construct models of the early universe that can generate gravitational waves that are largely consistent with the observations by the pulsar timing arrays. Here is one example. I will just explain quickly what this graph plots. This plots the spectral density of gravitational waves generated in a particular scenario of inflation. Okay, I told you the pulsar timing arrays the observations tell you two things. One is the Hellingsdowns curve. which tells you, essentially indicates that the background of gravitational waves that is affecting these timing correlations is stochastic in nature. And that's one part. And the other part tells you the amplitude and the shape of the gravitational waves in the early universe. Okay, amazingly, I don't have time to explain, but this model of inflation generates, these are the PTA, it can generate gravitational waves of adequate strengths that can explain the pulsar timing array observations. Here is yet another model where we have examined, you can again explain the pulsar timing array observations. This is prior to these observations. We are redoing these calculations to show how this can indeed explain these observations. There has already been adequate efforts in this literature in this direction. You can have scenarios, where this doesn't quite explain this, what are known as primary gravitational waves. There are different sources of gravitational waves in the early universe, and some of them are generated due to quantum fluctuations in the early universe, what is often referred to using the tensor to scalar ratio in the context of the cosmic microwave background. You can construct some primary gravitational wave scenarios. Here it is not able to explain the PTA observations, but you can modify some of this to possibly explain the observations by PTA. And here is a paper which appeared about a week back, where we have shown that you can have magnetic fields in the very early universe generate this is essentially where the PTA observations lie. And what we have shown is that you can have primordial magnetic fields that are present that can explain the PTA observations. The bottom line is that we have PTA observations which suggest a stochastic background of gravitational waves. And the open problem today is to understand what is the origin of these gravitational waves. I've said a lot of things in the last few slides, so this is a little technical, but if there are students who are interested, they can speak to me. I think I've already run over time, so I'll not talk about just that. One of the popular models, this particular model I talked about here, okay, is what happens to be the best fit model, to explain these gravity wave observations. And they are supposed to have occurred during the, these supposed to have been generated, these gravitational waves have been generated during the early stages of the radiation dominated epoch. So I will just summarize with an outlook. The observations by LIGO are a culmination of almost 50 years of global effort to detect gravitational waves. They are but a first step in a long process, and they open up a new window to observe the universe. I haven't talked about forthcoming gravity wave observatories, LISA, Cosmic Explorer, Einstein Telescope. There are many, many detectors that are being planned, observatories that are being planned, which some of them can even detect a mountain on the top of a neutron star. They are extremely sensitive telescopes, and gravity waves are indeed opening up a new window to our universe. And these have been complemented by indirect observations by the PTA and its implications for the stochastic background, gravitational background. They provide a wonderful opportunity to understand the physics operating in the very early stages of the universe. If you open up papers on PTA, there have been literally, every day there are a few models about to explain what is the source of the stochastic gravity wave background. We have been also contributing our 2 cents to it. And observations of gravitational waves, along with observations of electromagnetic waves, and hopefully neutrinos, will form, they are expected to be complementary in nature, and such a multi-messenger astronomy can lead to a deeper understanding of the physics of the very early universe. With those remarks, I will stop here. I apologize if I've run over time by about 5 to 10 minutes. I'll be glad to answer questions that you may have. Thank you.
Thank you, Professor Sriram, for that wonderful talk. So we can take a few questions and
Sure, absolutely.
comments from students or anybody.
Sir, you said gravitational waves move with the velocity of light. So how can we account for that? What's the reason for that?
What do you mean? How can we account for that in the sense?
How can we relate it
So
to?
there is an effort. I think there was one observation, where we actually had multi-messenger astronomy, where we observed the neutrons, combination of neutron stars and combination of, we observed the merger of neutron stars in the electromagnetic domain and also in the domain of gravitational waves. That allows us to put constraints by comparing those two events in different regions in the electromagnetic spectrum and in the through gravitational waves and through electromagnetic waves. It allows us to constrain what the speed of gravitational waves are. I don't remember the numbers. They are very, very strong. I can give you some references.
Thank you, sir.
Theoretically, if you ask what are gravitational waves in flat space time, and you ask what should be the velocity term that appears in that equation, it's a velocity of light. So there is nothing to suggest, at least in simple theories. In modified theories of gravitation, the speed of gravitational waves can be different from speed of light, but in Einstein's relativity, gravitational waves propagate with the speed of light. And as far as observations, to the extent I know, what we observed is consistent with general theory of relativity.
Sir, if I throw a steel ball to the ground, and you can see that in successive falls, the frequency of the hitting increases. If I throw a steel ball into the ground, so is that similar to what is chirping is happening in the black hole? That the same gravity effect is doing in some other way, like the number of it's almost the frequency is increasing exponentially. Okay, if I throw a steel ball into the ground, you can see that at each instant or each successive hits, the frequency of hitting actually increases with time, almost like a chirp.
Complete your question.
So you can see almost like a chirp in the frequency of hitting.
Oh, chirp.
Yeah.
I think it is too, you are trying to relate to something that you're familiar with. It is just, I think it is just because what is happening is the strength of the gravity wave, in some sense, what is happening? Gravity waves are being emitted as these black holes are merging together, as you saw in the movie. As they are coming together, they're moving faster and faster. The time period is increasing. In some sense, the time period of the emitted gravitational wave should depend on the frequency of their motion. Correct? So as they are coming together, their frequency is increasing, and therefore the emitted frequency also increases. Since they are closer and closer, the strength of the gravitational waves are also increasing. It is not clear to me that there is a direct relation to that example that you're quoting.
Hello. So the stochastic gravitational wave background has the same polarization as the merging black hole.
No, it is okay. So you have to be careful. In the context of merging black holes, we are broadly able to understand which direction of the sky we are, we are able to understand the source. We need one more detector to be able to identify the source very precisely in the sky. That's one of the challenges today in gravitational wave physics, is to pinpoint the source in the sky. A stochastic gravitational background, by its statement, it implies we don't know the direction from which it comes from. Stochastic means it's random. Okay. Yes, but merging black holes can contribute to the stochastic background. It's random. Okay. If you are not able to identify the source, you term it as stochastic. But if you are able to identify the source, you know what it is and you actually remove it. I hope you understand what I'm saying.
Yes. So if there is a beat, the circular beat, and if the stochastic background hits the beat,
sorry?
That circular beat shaped thing you showed.
That is right.
So if the stochastic wave hits that beat,
Right, it will just oscillate. It depends on the polarization. It'll just oscillate in the manner I described. That's all. Stochastic just means um, we it is random. There is no pattern. Look, okay. If you have, let me carefully explain what I'm trying to say. If you have one merging black hole, we roughly understand its waveform. What do you mean? What do I mean by waveform? That h of t. I will explain what h of t is, plotted as a function of time. You saw at the bottom of, I highlighted the bottom of one of the videos, right? We know how it occurs if I have a merging black hole somewhere. And even if it's a large black hole, I should be able to model it. But imagine a situation where there are 10 black holes simultaneously coming and hitting my detector. I will not be able to, remove these waveforms separately. All I know is that there is something completely, the behavior of this waveform will have no correlation with the behavior of this waveform. Okay? And I have multiple such waveforms, then I will refer to as a stochastic gravitational wave background, because I'm not able to identify the source or identify a specific waveform that contributes to the detector's motion. So imagine, it's like if you have one such waveform, it would have moved in such fashion, all right? But if you superpose multiple such waveforms, they will behave a little crazily.
So we cannot detect that stochastic wave with the LIGO detector or...
No, that's the point. We will be able to detect, but okay. There is a question that is often asked whether LIGO detectors have also seen a stochastic gravitational waveform. I think this is a non-trivial answer to that. Okay, there is a background. As I said, everything that's happening emits gravitational waves. Okay, so the question is, what is the dominant source of this stochastic gravitational wave background? And LIGO is able to, okay, I'm going into a domain which is not quite my area of expertise. But what happens is that LIGO is sensitive to, actually, at some point of time, they were detecting something very regularly. And they found it's a lorry which is going over a bridge or something like that, a truck going over a bridge. So it is sensitive to many such disturbances. Okay, so I think LIGO is able to detect waveforms which we know a priori. So it's done using match filtering. There is a lot of effort that goes into modeling the waveform. If you go through gravitational wave literature, there'll be hundreds of waveforms. And what they do is that they have a bank of waveforms. They have a signal. They do what is known as match filtering, as used by electrical engineers long back. Okay, and see whether there is a correlation. So, but stochastic gravitational waves don't have such a specific waveform. They are random. And therefore, getting it out of LIGO at this stage is a bit of a challenge. I hope I've been able to answer your question.
Yes, sir. Thank you.
So, how energy momentum conservation leads to quadrupole?
Or no dipole radiation. I have to speak to you separately. I can show you what happens in the context of electromagnetism. There is a discussion in Griffiths, and I will request you to reproduce. If you have done a course on GR, I'll request you to reproduce it in the context of GR. Okay? Yeah. You ask, why is there no monopole radiation in electromagnetism?
Polarization in the case of electromagnetism is the direction of the electric field, right? What is the quantity in the case of gravitational wave?
It's the it's the components of the metric tensor.
Yeah, but it's a tensor.
It's a tensor, yes.
Can you identify it with a vector?
But,
some
sorry?
Some vector you can identify it
but polarization, Electromagnetism is a vector theory. Gravitation is not.
No, no, but polarization, you identify it with the direction of the electric field.
That is in the context of electric fields,
Yeah, yeah.
in the context of electromagnetism.
So is there anything similar in gravitation?
Okay. I'm trying to. It's transverse in both the cases.
Yeah,
that
that's
is
another question.
the oscillation. Sorry.
Transverse question.
Yeah, it is. It is the oscillation occurs. Now you have to ask what is oscillating, right?
Yes.
We know what is oscillating in the context of electromagnetism. It is electric and magnetic field. What is oscillating in the context of gravity? It is the metric components of the metric tensor itself. So it's somewhat different. You have a polarization tensor to describe polarization in the context of gravitational waves. You have a polarization vector to describe electromagnetism. There are similarities, but there are important differences. This is the nature of the theory. It's the nature of the fundamental quantity in your theory. In the context of electromagnetism, it's your vector potential. In the context of gravity, it is your metric tensor.
Yeah, but if you think about polarization, right? Even electromagnetism, if you have a boundary, not in a finite region, electromagnetic wave need not be transverse, right? Like in wavegates.
So now you are talking about interaction. I understand your point. I am not able to immediately comment about. Now you are talking about propagation of gravitational waves in a medium. I can roughly think how I can describe them. I need to describe the medium as modifying the space-time and the gravitational waves propagating in that. And I'm not able to say what could be the consequences, immediate consequences, like you may encounter in the context of electromagnetism. But you can carry out similar exercises is what I can see. Okay, thank you.
Hello, sir. Connected to that question, so you mentioned the gravitational wave is a linear polarization. We have plus and cross polarization. So could you explain when we get this plus polarization and when we get this cross polarization?
What do you mean when? What sources will generate one and what sources will generate the other?
Yeah, yes.
I'm not able to say immediately what should I do to generate one type of polarization or the other. In general relativity, both polarization in any mechanisms, I can tell about what I am comfortable with. In the early universe, they will generate both types of polarization with equal strength. In early universe physics.
Here plus and cross means is a stretching and squeezing.
Right.
Okay, so can we detect then from the strain of the interferometer or?
So yes, so I think at this stage they are not in a situation to detect incoming polarization. I think the sensitivity is not. No, they are not able to detect the strength, the polarization components. If that is what you're asking, they are not able to detect it. The polarization we are not able to detect, because if we are able to detect polarization, there are other we can constrain many aspects of relativistic theories of gravitation. We are not able to yet do that, is what I understand. But if you are, I can think of, if I'm generating gravitational waves in the early universe through quantum fluctuations, they will generate them in both polarizations with the equal strength. There is nothing to break the symmetry between the polarization. Very much like what you will do in the context of electromagnetism. If you want polarizations to behave differently, you need to violate parity. Okay, so there are parity violating theories of gravity as well, but in general relativity is not one of them. So I would imagine mechanisms will generate, to the best of my knowledge, gravitational waves in both polarizations of the same strength.
So and we are only these two polarizations are possible.
That's a question. I think there can be. I'm not able to sweepingly say that, these are the only polarizations possible in all theories of gravity. I think there are theories of gravity where there is an additional degree of freedom that can be present. I'm not able to comment about it further
When we
now.
read, we see only plus and this cross polarization.
Sorry.
When we read the articles, we see only this plus
In
and
most of the theories of gravity, which is in certain, I can think of, Einstein's gravity is just root minus gr. I think if I have f of r gravity also, you will have only these two types of polarization. And yeah,
Thank you.
there can be more complex theories, theories of gravity, where can be there can be a parity violation. All right, whether it introduces additional degrees of polarization, I'm not able to comment about it.
First of all, thanks for this neatly articulated and beautiful flow through the topics. Now, one clarification I seek is this stochastic gravitational wave background is still astrophysics in origin.
Sorry.
The stochastic wave background is still astrophysical in origin, not cosmological.
No, but that's what I'm trying to say. I'm constructing models which can be, in fact, it suggests it's not astrophysical.
So it's beyond doubt?
Yes?
It's beyond doubt or still a proposal?
I don't know what you mean by astrophysical. Where do you draw the line?
Astrophysical means maybe black holes or pulsars.
So the one of the popular models are merging supermassive binary black holes. They are not doing a very good job in explaining the data. One of the best models that explains the data very well with a significant Bayesian evidence, right, is this guy here. Okay, is what is known as, essentially when you have what are known as ultra slow epochs during inflation. So what essentially you need is a sharp rise in power on small scales. You choose your inflationary model to do that. They can explain the data well.
Okay. Now, another question I have. So when basically you are writing down Einstein's equations, you are using Einstein's tensor, which is a contracted version of the fourth rank tensor, Riemann tensor.
Right.
So when you are contracting it, some components are gone. Say, what I'm exactly pointing out is Weyl tensor.
Okay.
Weyl tensor.
Okay.
So, is it possible to use it to describe some sort of empty space gravitational waves, something like that? Maybe a speculative.
So, look, the Weyl tensor is often used to relate. Understand whether two different metrics are related by a conformal transformation.
Yes.
Now, if you have a gravitational waves, I cannot conformally transform it to a flat space time. I mean, there are gravitational waves present. So I do not know how the Weyl tensor, there may be some other use, but if you are thinking along the lines of my first statement, there will be a non-zero Weyl tensor associated with even with gravitational waves in flat space-time.
Okay, we will discuss.
Okay.
Hello, sir. Hello.
Yeah.
Thank you for the wonderful lecture.
I'm glad you enjoyed
yes. The one basic question regarding the experimental observation of the chirp.
Right.
So you told that two black holes, the binary system, when they kind of make that merger, the frequency of the gravitational wave is increasing. So my question is that in the detector, I mean, this event might have happened, I don't know, means maybe
billions of years ago.
Billions of years ago. Means how has it happened that they were looking for this particular event to pass by, or like?
No. We are, as an astronomer, we don't have the luxury of an experimental physicist to tweak my table, the experiments at my table. We just have to, turn on our detectors and wait, turn on our telescopes and wait, and we are fortunate enough to, observe something. It's amazing that when the detectors sensitivity were raised, I think just before this date. I don't recall the exact history. I'm sorry about that. But I think they had raised the sensitivity of the telescope and they turned it on. And this is one of the first events they detected. So it is just fortunate, extremely fortunate. So I don't think they were, waiting for this to happen at that time. They just turned on the detectors. In fact, we have been told it's not a detector, it's a gravity wave observatory. We are observing the universe through these observatories, and the gravity wave hit. And I should mention, probably I did not emphasize adequately, since the original detection, there have been close to 100 such detection of various, mergers of binary black holes. But if to my understand right, only one neutron star merger. Okay, so there have been many such events, and as the sensitivity of the detectors go up, I was hearing, someone from B.S. Satyaprakash speaking recently, how we are going to detect one every, few minutes and so on as we proceed with the sensitivities of the detectors going up. In the detectors that are being planned in 20 years, Cosmic Explorer or something, they will be hitting you very regularly. So that was just fortunate that it happened quickly. As soon as the sensitivity went up, there was this extremely bright event, so to say, that was picked up by our detector.
So they could direct the position of
no, that is a challenge. That is a challenge. I am not able to comment about it. Yeah, from what I understand, you need two detectors. You can just broadly say where the source of this is, but with 3 detectors, you will be able to, do it much better. That's why a detector such as LEGO India becomes very important.
Thank you, sir.
You're welcome.
Maybe a couple of questions more.
Sir, so the detection of these gravitational waves by LIGO and such, so does it have any implications on the theories being put forward to explain the unification of fundamental forces?
No. This is still classical gravity. Please note, the unification is related to quantization of gravity. What is a quantum theory of gravity? Gravitational waves that we are talking about, I will make a correction to that statement. Most of the gravitational wave we are talking about are classical solutions to my Einstein's equations. There is one part where there is a quantum gravitational wave that comes in. If I'm not able to answer, you can speak to Professor Titus Matthew, okay, where you can have fluctuations during inflation, which originates from the quantum vacuum. These are known as primary gravitational waves. And that is close to quantum gravity. Whether you are seeing truly quantum effects of gravity is something people will debate, but that's the closest to a quantum version of gravitation that you are encountering. We are still trying to understand what is the correct classical theory of gravity. Quantum gravity is still remains a dream.
So in the future, can we someday harness the power of gravitational waves that now we do today with electromagnetic waves?
Yeah, I was just, I was teaching a bunch of electrical engineers last semester. I was teaching physics 101, and I was teaching mechanics and so on, and I was telling them about Lagrangian formulation. They were, one of the students asked me, what am I doing? I mean, I know Newton's law, it works well. Why do I need a Lagrangian formulation? So I was telling the student that, look, I work on issues such as these, which are far more abstract. Maybe there will be gravitational engineers instead of electrical engineers one century down the road. I'm not able to comprehend, what can happen. Gravitational waves are incredibly weak. So I do not know how I'm going to harness something which is so weak and which are generated by large masses, etc., sitting on the earth. Maybe, maybe I'm not being imaginative. I can imagine that maybe a gravitational century instead of an electromagnetic century, a year, 100 years back, 19th century saw the development of electromagnetism, and 20th century saw the quantization of electromagnetism. So we are trying to converge on a theory of gravity. What is the classical theory of gravity? Maybe we'll come with a quantum theory of gravity, and there can be, there may be many possibilities. My limited abilities does not allow me to see very far.
Thank
Maybe
you, sir.
youngsters, that's why youngsters should take up and work on them.
Thank you, sir.
Pleasure.
Maybe when you do interstellar travels, your spaceship can harness power.
So yeah, so maybe you have an Einstein-Rosen bridge, wormhole, etc., etc. There are many possibilities. Yes, Charles.
Sir.
Yeah, there's some question. Charles, have been waiting, and then I'll be back. No, go ahead, Charles.
So can pulsar timing array distinguish between the contributions to the signal from primordial as well as astrophysical sources? Alone.
So now this is related to what Titus was also asking. So no, it can see only the sum. I can show you the equations. So what happens is, what is amazing is that the Hellingsdowns, it's a product. This correlation function. What did I say? You take the time period of the pulsars, right? And you see what's the difference between the actual arrival time and the time period. You call it delta t. You construct delta t by t, okay? And you construct at every sequence. And you have this sequence for one pulsar for 15 years. Now you start correlating with every other pulsar like this. These guys have been working for 15 years now. Now, amazingly, when you cross correlate, it divides into two parts. One, which depends on this Hellingsdown curve that appears there, and another, which depends on the strength of the gravitational waves. So the assumption that goes into this derivation is that it's a stochastic gravitational background. We are not sure of its origin. It could be what may eventually happen, as with anything in the world, there may be multiple contributions. You understand? It could be a sum. Okay, that's the first part. We do not know. But if you ask what fits the data very well as it stands today, well, it seems to be some primordial gravitational waves.
So, how can we make use of these gravitational wave observations to detect dark matter?
Maybe lensing of gravitational waves. This is something I haven't thought about much, but just like lensing, lensing of electromagnetic waves, you can use to constrain, these objects called machos and things like that, small objects, in the halo of our galaxy. As you are observing some faraway object. There are extremely tiny Jupiter-sized objects in the halos of galaxies, etc. And they will. What happens is that as they go through, so you are observing something, and imagine the macho is going through for some reason across. So there will be a brightening and dampening of light. Now imagine you're observing gravitational waves. And in principle, there can be lensing of gravitational waves by intervening dark matter. And people are discussing lensing of gravitational waves. But there are crucial differences. There is often substantial difference between the wavelength of light, which is very small, compared to the lensing objects which length. Okay? But that's not quite true in the context of gravitational waves. Okay, so you cannot work in the geometric optics approximation. I hope you understand what I'm saying. The wavelength of light is much smaller than the objects which lens. Okay, so you can use ray optics in the context of electromagnetic lensing of electromagnetic waves. But that may not always be true in the lensing of gravitational waves. And there is a huge new direction people are investigating. P.Ajit at ICTS have been talking about lensing of gravitational waves for some time. So that's one possible way of detecting dark matter. There may be other possibilities. I do not know. I can dream of something. So what happens is that when you It's not detection. When you enhance power, like, when you do this in the context of early universe, you end up producing what are known as primordial black holes, which can be dark matter. So there is some indirect connection, but the only direct way of using gravitational waves to detect dark matter is lensing. There may be other possibilities, possibly discussed in the literature, but I'm not able to comment about it further.
Thank you, sir.
Thank you. And he will be available from 2:30 to
Absolutely.
4:30 in the head of the department room. And if you want to interact or say hi to him, please drop in. Okay. So we'll wind up. And so on behalf of the Department of Physics and Academy of Physics teachers, I'm really thankful to express my sincere gratitude to him for the excellent session. And I'm sure it's a very apt tribute to Professor Valsakumar. So that's it. So we'll break now. And if you want to meet him, please drop in after 2:30.
Thank you.